Alright, so this is the solution video for the Mr. G worksheet for 11.2 power generation and transmission. Okay, so first question, what is the peak voltage of a rectangular coil of wire having dimensions blah 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 blah. There's a couple things I want to say first, and then we'll get to the given information to actually get some numbers down. But how to get peak voltage or the peak EMF, and I want to talk about EMF as a function of flux and the derivative of cosine. Okay, so first of all, and we know that EMF is the derivative with respect to time of phi. But there's one detail, I keep on talking about that, and there's one detail that I was leaving out. It's like derivative with respect to time. Where's time? Time's not in that expression. So it actually is. We have to remember that theta is omega times time. And the reason why that's true, remember that omega is 2 pi times the frequency, or 2 pi over the period. And so we wind up with 2 pi over the period times the time. Now, if we're talking about the period's the time for one cycle. So really this t, the lowercase t on the side, is specifically the period. And if we're talking one cycle is also 2 pi. I have no idea what's going on in physics class. So they're doing some kind of trivia game. But so yeah, one cycle is 2 pi, and the time for one cycle is period. The period cancels, and really you're just kind of saying theta equals theta, or theta is 360 degrees or 2 pi when we're talking about one cycle. So yeah, theta is omega t. Now the reason why that matters is because I can rewrite this flux expression as NBA cosine omega t. And so if I take the derivative of that, the derivative of cosine omega t is negative omega sine omega t. So yeah, there's our EMF as a function of time instead of as a function of angle. And now what it's asking for, it's not asking for EMF, it's asking for peak EMF. So, and that EMF is at a maximum when the sine of omega t is 1 instead of 0. So if we set sine of omega t to 1, then therefore we have EMF is negative NBA omega, or EMF max is negative NBA times the angular frequency. And of course, omega is 2 pi times the frequency. We said that before. So we're going to use the frequency they gave us, the magnetic field they gave us, the number of turns, and then we also had to figure out the area. So let's do that. Let's use this 4.5 centimeters by 6.8 centimeters. So that's 3.06 times 10 to the negative 3 meters squared for our area. So let's work the numbers. Working the numbers through, we get 389 volts, really 3.9, maybe 390 volts because of the two significant figures on our givens. Maybe I'll write that in, 390 volts. Number 2, write an equation of the time dependence of its EMF. Hey, I already did that. It's right above it. All right, that's done. Number 3, if you decrease the frequency to 40 hertz, what is the peak voltage? So I can see that the peak EMF is directly proportional to frequency. So I don't know why they picked 40 hertz instead of, say, 30 hertz. 30 hertz would be half. 40 hertz is not half, it's 2/3. But at 2/3 the frequency, it would be 2/3 the peak EMF. And so 2/3 of 389 and change is 260 volts. Next question. We have graphs of EMF versus time in milliseconds and current versus time in milliseconds. Okay, so starting with 4, we have two graphs. We have an EMF graph and we have a current graph. And then 4 says find RMS voltage, it goes with the graph. 5 says find the peak voltage. I don't know why they didn't do peak voltage first, because RMS voltage depends on peak voltage. So I'll actually do 5 first, and it's pretty easy, because peak voltage is just the max voltage that is shown. I just realized something. The scale for the positive voltages is different than the scale for the negative voltages. I think that's got to be a mistake. Nobody actually scales their graph like that. So then, kind of looking at this right here, instead of -20, I'm going to call that -10. And then instead of -40, I'm going to call that -20. I think that would make more sense. Then, all right, so peak voltage is either +20 or -20, but I would call that 20 volts for the peak voltage. And so VRMS is peak voltage divided by radical 2, which is 14 volts. And so that's the answer number 4. Peak voltage was taken right off the graph, so there's that. Angular frequency of the coil producing this EMF. And so that we can actually get from the time for one cycle. I can see that the time for one complete cycle is 10 milliseconds. And so that's 2 pi over the period, which gets us 628 hertz, which if we round for sig figs is 630 hertz. And then the flux linkage is n times the flux, which is NBA cosine theta. For the maximum flux linkage, that cosine theta would be equal to 1, so the maximum flux linkage is NBA. Now that's great, but we don't know the number of coils, the magnetic field strength, or the area of the coil. We do, though, have a graph of EMF versus time. So what we might actually need to do, but we do know from number 1 that maximum EMF is equal to negative NBA omega. And we just found omega. And while we don't know NBA, it's what we're solving for. And we also know the peak voltage. So NBA, which is what we're looking for, the maximum flux linkage, is equal to negative max EMF divided by the angular frequency, which is why they had us find these things in 5 and 6. And so then we get 0.032 volt-seconds, or Tesla meters squared. Okay, let's get RMS current from the graph. And we find RMS current the same way that we find RMS voltage. And again, I don't know why it's asking for the RMS before the peak, because you need the peak value in order to get the RMS value, but whatever. So 8 and 9 are very similar to 4 and 5. Then we need current versus time, so we know that the relationship between voltage, current, resistance. So if R equals V over I, then I equals V over R, and we have the formula for EMF as negative NBA omega sine omega t. And so if I is V over R, then the current would be I would be the EMF over the resistance, or negative NBA. Oops, I missed the omega. Omega sine omega t over the resistance. At least I think that's what they're looking for. It does follow a sinusoidal pattern, and it is current as a function of resistance. And it kind of follows the same pattern as the voltage, it's just that the values are moderated for current because of the resistance. And in fact, number 11 wants you to find the resistance of the circuit. And so if R is V over I, 20 volts max voltage over 2 amps max current is 10 ohms. Or are we supposed to use the RMS values? Let me look into that 1 second. Oh, and of course, it's a relationship. So whether we do 20 divided by 2 or 14 divided by 1.4, we still wind up with 10, of course. So 11 is 10 ohms. Now 12 is where RMS makes a difference because it doesn't want the maximum power in the circuit, it wants the average power in the circuit. And you get about 19.6 watts, which running for 2 sig figs gives us 20 watts. Also on the data booklet, average power is given as half of the maximum V0 and I0, but this is the whole point of RMS. We find that when we do half of the product of the maximums, we still get 20 watts. So that's how RMS does represent an average of the values. All right, let's move on. And here we have transformers. Okay, so the formula for ideal transformers is just a ratio of the EMF or the voltage to the number of turns, and the greater the number of turns there are, the greater, like the voltage ratio, I should say, is equal to the ratio of the number of turns, but that's inversely proportional to the current that you get. So that's all gibberish, unless you look at the actual equation from the data booklet. So the EMF of the primary coil over, like, the ratio of the EMF of the primary to the secondary is equal to the ratio of the number of turns in the primary to the number of turns in the secondary, but that is equal to the ratio of the current in the secondary to the current in the primary. So, I mean, you can, why am I even describing it? I just wrote the equation. You can see it right there in front of your face. So this is not asking about the current. In fact, number 14 is asking about the current. It's just asking about the turns and the voltage. So in that case, we don't need the current relationship. We just need the turns and the EMF. And to be clear, primary is the first coil, and it's the input coil, and the output coil is secondary. And so we get 232 turns in the secondary coil for that guy there. Now, let's take a look at the currents. There we have it, 0.781 amps. Okay, next question. I'm not sure what number 15 is getting at. Is it explain the use of high voltage step-up and step-down transformers in the transmission of electrical power? I think what they're trying to say is, why is high voltage used in transmitting electrical power as opposed to low voltage? All right, so energy will be conserved. So the power will be the same no matter we use high voltage or low voltage or whatever. It's going to be the same power, but we want to actually deliver that power to the customer or to the endpoint. We don't want to lose power in heat losses along the line. So we actually want to deliver energy in the form of electrical energy, not in the form of electrical energy minus massive quantities of heat. That would be dumb. So in any case, let's remember that power is the product of voltage and current. And the more current we have, the more heat losses we have. So the amount of actual current, quote unquote, flowing through the wire, there's going to be greater heat losses. So we pretty much want to transmit, in terms of the power, we want to have a large voltage and a smaller current, not a low voltage and a higher current. And so, yeah, you want high voltage and low current. So that's why we have step-up high voltage transformers to transmit the power over high voltage lines with less current. It's going to be the same power delivered. The reason why you see signs that say danger high voltage, and when you're thinking, it's like, actually that should say danger high power. It is high power, but it's also high voltage, and so the voltage is controlled by the use of transformers. But if you were to touch a high voltage power line and ground it, suddenly there would be a massive potential difference between that high voltage line and the ground, which is at a potential of 0, and then that completely destroys the point of having the high voltage line. Now you have a short circuit, and all of that power then goes coursing into the ground. The current spikes, and then you do have heat losses, things are exploding, and et cetera, et cetera. And the reason for the explosions, like for instance for transformers, those are like the cylindrical cans you see up at the top of power lines. Those are transformers. Usually, if they're transformers near your house, those are step down transformers from the high voltage lines to the lower voltage lines that are going to your house. And if they explode, and sometimes they can explode even like near your house, there are videos of that sometimes show a transformer exploding. If there's a short circuit inside of the transformer, or if the insulation in the transformer fails, creating a short circuit, then you do have a spike in the current. The temperature rises rapidly, then that vaporizes the insulating oil inside of that container. Yes, there's oil in there, serving as an insulator, but that oil can be vaporized, become explosive, and boom, there goes the transformer in a big shower of sparks, and everyone is really annoyed because that means the power is going to be out for a while as the power company fixes that problem. So there's usually not that much danger from an exploding transformer, but it does mean your power is going to be out for a few minutes at least. And by a few, I mean a lot of fews. Fuse? See what I did there? No? Okay, let's move on. I don't like number 16 because it talks about that the power plant makes an RMS voltage of 125 volts, and it wants to step that up to 765,000 volts. But it doesn't say if that's a peak value or an RMS value. And it matters because the ratio of the secondary coils to the primary coils is equal to the ratio of the voltages, and the RMS ratio and the peak voltage ratio should be roughly the same. I'm honestly not really sure that it matters because the maximum value for the VRMS 125 volts, the V naught, the V max for that is 177. But if you're doing a ratio of either 125 to 765,000 or 177 to 765,000, there really isn't much of a difference. So I'm not sure it matters. Okay, so 17. A little bit of a throwback to properties of a conductor. So there's our area, and then rho is RA over L. That's from topic 5.2. So they gave us the resistivity. We just solved for the area. And we do have the length, 375 kilometers. And we get 0.260 ohms. My numbers are not making a ton of sense. I just double checked my numbers. My area is actually wrong. It's close but wrong. Instead of actually it's not close. Instead of 0.07, it's 0.001. Changing the area changes the resistance, brings it up to 11 ohms. It still gives us a lot of current though. 5,000 amps? I have to use the transmitting voltage to get the current. Because okay, let me do VI. That's still high, but it seems reasonable. Now that we know the current in the wire, then we can figure out how much power, how much heat loss, I squared R, is generated in the wire. So it's about, it says 153.0419, it's about 1.53 megawatts of power. So of the 285 megawatts that's being attempted at delivery, it's losing 1.53 megawatts. So what percentage of that? So even though it's losing about 1.5 million watts of power to heat losses along the length of the wire, That's less than 1% of the total energy, so that's not too shabby. Okay, and last but not least, we have our diode bridge, which is used to turn AC alternating current into direct current for transmission over wires, over power lines. Okay, so if we're going to call this the top side positive and the bottom side negative, this actually says red pencil trace the positive current. All right, that's opposite than the lab we're going to be doing, but it does ask for red. So, okay, positive is red, and then negative is going to be green. So we go from the positive terminal coming across here, and then we have positive, and then it stops at that diode because that's not the correct direction, and so, but the positive does transfer this diode up to the load, and this creates a positive terminal here. Now, in terms of the negative, remember that the direction of diodes show the direction of the positive current flow. So then for negative, the negative voltage, it actually stops. You'd be like, oh, wait a minute, why is it stopping like right here? And because that arrow, that shows the direction of the positive charge flow. We're talking about negative voltage, so it actually stops there and goes through that way, because it's like, well, no, the arrow is pointing in the wrong direction, right? But this is negative we're talking about, so it's the opposite. All right, so then that gets us down, going this way, going that way. That makes a negative terminal on that side, and it goes to the load. I also, here, I don't know why that didn't go there. All right. And so that's 20 and 21. But 22 says if the AC power supply reverses polarity, what happens to the output terminals? Output terminals are going to remain the same. That's the entire point of a diode bridge. Let me show you why. So yeah, that's the point of an alternating current, is that the positive and the negative terminals alternate. But notice that I left the original positive and negative terminals, I left those there, and you're going to see that they stay the same. Let's trace it. All right, so let's start with the positive. Positive's on the bottom now. So positive's coming along, la la la, and then it tries to go up to this diode. Diode's like, nope, no way. So we can pass through this guy, that's cool. And oh, will you look at that, we wind up with the same positive terminal. Let's try with negative this time. So negative comes around, la la la. And now remember, the diodes are drawn for positive voltage, so the negative actually stops there and travels this way. La la la, travels through this way, this route, hits my load, my resistor, and then, oh, it goes to the negative terminal. So it doesn't matter with the alternating current, whether it's negative positive or positive negative, the DC output, because of the diode bridge, always remains the same. That's the point. Okay, and that is the last question on this 2-page Mr. G document here. And the last thing in topic 11.2, which is diode bridges. And thank you very much.